Okay, I'm going to do a screencast here. I give you some examples of conservation of energy. I'll do a couple iBook problems, but I wanted to start off with one that kind of shows you how conservation of energy can compare to kinematics in solving problems. Because up until now, if I gave you a problem like the one that I drew on my screen right here, which is a guy dropping a rock off the top of a cliff, and I didn't use any numbers here. I've just got in here that the person is dropping a rock. So the initial velocity when you drop something, you remember, is 0. The height above the bottom of the valley is h. And I want to know how fast is that rock going just before it hits the ground. That's the question. So how fast will this rock be going when I drop it from a height h? Let's just assume the mass of the rock is just m. So again, I'm just using letters. I'm not using numbers. If this was kinematics and I gave you initial velocity, I gave you the delta y. That's what the h is here. That's the delta y. And I asked you for final velocity. And you would say to yourself, well, I know the acceleration is, g in the negative direction. And I said, what's that final velocity? You would use Mr. Fantastic, if you remember that, on that whiteboard, in our class. Mr. Fantastic looks like this. And you would solve for VF, okay? And you'd get an answer. No problem doing that. Let's think about this from the perspective of energy, though, conservation of energy. So we're going to assume there's no air resistance, so there's no mechanical energy lost to the rock heating up as it falls, which is what happens with air resistance. It causes things to heat up even just a little bit. So let's assume no air resistance. So at the beginning of this problem, first of all, let's define where 0 is from a gravitational potential energy standpoint. And I always recommend putting 0 at your lowest point. So I'm going to say my PEG 0 point is at the bottom. Just before the rock hits the ground, we'll say when it gets to that point, it has no gravitational potential energy. So when it's up here at the beginning, it has a lot of gravitational potential energy. So it's got some PEG initially. So that's what kind of energy it has at the beginning. Then at the end, since my gravitational energy is 0, all of that gravitational potential energy gets converted into kinetic. So I've got all this kinetic energy down here at the bottom. So basically that long equation that's got, PEG initial plus KE initial plus PE elastic initial equals PEG final plus K final plus PE elastic final. There's no springs, I get rid of that. There's no initial kinetic energy and there's no final gravitational energy, so it's just PEGI. All of that gets converted into kinetic. So then let's go through and solve this problem for the final velocity. Let me substitute in my equation for gravitational potential energy and kinetic energy. And remembering that I want to solve for my VF, right? I know mass can cancel out because it's the same mass of the rock on both sides. If I solve for VF, my final velocity is equal to, I multiply this side by 2 to get rid of the half. So I get 2GHI, and to get rid of that square, I have to take the square root. So it's equal to 2 times the g, the gravitational constant, 10 meters per second squared, times the initial height. So basically h. Well, think about Mr. Fantastic. Had I solved for VF here, knowing that this is 0, I would have gotten square root of 2a delta y. A is just g, and delta y is h. It's exactly the same answer as I just got down here, which is a good thing. You would expect that because I shouldn't get different answers depending on whether I use kinematics or whether I use energy to solve a problem like this. If I want to find that final velocity, you might actually think energy is the easier way to go as opposed to using one of the Fantastic Four, which is, an equation. You got to substitute all those numbers in. This is a really easy equation right here. But you get the same exact answer. So you might ask the question, why would I use one versus the other? Why use energy if I have kinematics? Why use kinematics if I have energy? Well, remember all these quantities in kinematics. The Velocity, the displacement in the y direction, the acceleration, those are all vectors. They have magnitude and direction. Energy is a scalar quantity. It can be positive or negative. It does not have direction. So if you care about like what angle if you're shooting a projectile and you want to know what angle it is at when it is about to hit the ground, you have to use kinematics to answer that question. You can't use energy to solve a question where angle or direction is important. But for something like this, to find the final speed, final velocity, energy works fine. Okay? Let's do a couple problems that are assigned for homework tonight just to get you started and kind of understand how to do them if you're getting stuck a little bit. So this is number 37 out of your iBook. I think it's on page 298, maybe 298, 299, something like that. It's a 215-gram particle, and it's released from rest at point A. It's inside a smooth hemispherical bowl. So what that means is it's in the shape of a sphere, but it's only half of a sphere. And they give you the radius of that sphere is 30 centimeters, and they tell you to calculate the following. The gravitational potential energy at A relative to B. Well, they use that word relative. That means what's the difference between the two. I would call B my 0 point. So then all you have to do is figure out the vertical distance between A and B, and it's pretty obvious that's the radius of the bowl. So that one is pretty easy to figure out the difference in the gravitational energy between A and B. So I'm not going to spend too much time on that. But what might be interesting is potential energy and kinetic energy at C. Because if you think about this, if we assume there's no friction here, that's the big assumption here. The assumption in this bowl is there's no friction. So let me just write that down. So all your mechanical energy is going to be conserved. So all this PE, gravitational, that you have at the beginning, when it gets down here to the bottom where PEG is 0, 100% of that has to be converted to kinetic. Now, if this were to rise back up again, all the way back up to a point up here that's the same height as A, I would have all PEG again. But you see at point C, it's not that far up. It's only 2/3 of the radius above that point B right there. So in fact, you have a little bit of, at point C, you have some gravitational potential and you have kinetic both. Your job is to figure out how much of each. The total sum of those two is exactly the same as how much gravitational energy you started with or how much kinetic energy is down here at the bottom. The total amount of mechanical energy isn't going to change. It's just going to be divided up between these two forms. So my recommendation is use this dimension right here to figure out how much gravitational potential energy you have at point C, and the rest of that energy that's left over of the total has to be kinetic. Okay, I hope that helps you with 37. Let's look at number 41. 41 is a problem where it's got Tarzan and Jane. And their total mass is 130 kilograms. So I'm going to say M total is 130 kilograms. And they have a 5-meter long vine. And the vine is at an angle of 30 degrees with the horizontal. I would always, always, always tell you guys to draw pictures. And, I mean, you don't have to draw pictures of the two people. I'm just going to put a mass out here because we're going to treat Tarzan and Jane like point masses. Okay, so this thing is at an angle of 30 degrees with the horizontal. Okay, I was going to make it from vertical. So that would be a 30-degree angle here. And their mass is 130 kilograms. They're going to swing down here. At the bottom of the arc, Jane, whose mass is 50 kilograms, so mass of Jane is 50 kg. She releases. So now from here up, you've got only the mass of Tarzan. So he must be the difference between those two, right? He must be the 80 kilograms that's left over. So they want to know what's the maximum height to which Tarzan can land on a branch after his swing continues. So the question is, how high can Tarzan go without Jane being on, on the vine as well? So this is an energy problem. You're going to want to start with gravitational potential energy. I would call this my zero right here. This is where your PEG is zero. So if they both start from rest, then your kinetic energy at this point, at the beginning, is zero because you're starting from rest. And how high can Tarzan swing? Well, at the end here, that would mean he would have that would be at the very apex of that swing. So he would have no kinetic energy at that point either, because just for an instant, you're stopped. So that would be final kinetic energy at Tarzan. So the question is, how much energy do we have at the beginning right here with the two of them, 130 kilograms above this bottom point? And then some of that energy from the beginning gets converted into kinetic for Jane. So we got to figure out how much goes off here with Jane, and then how much is left with Tarzan at the end. So the first question is, how much energy do you have at the beginning? Well, you have some gravitational potential, but you need to figure out how high you are above this 0 point. You got to find this delta H right here. That's the key, is that delta H. And if you notice, I've got a 5 meter long, they gave me the length of the vine up here, a 5 meter long vine right here. So this distance from here to the bottom here, that's 5 meters. And I know this is 5 meters right here. I'm going to go to the end of the ball right there. So that's 5 meters right there. The question is, how long is this side right here? And you can use trig to figure out that. If I know this is 30 degrees, this has to be 60 degrees. So I've got a 60-degree angle. I've got a 5 meter, oops, that's not the one I wanted. Sorry about that. I've got a 5 meter hypotenuse. So I want to figure out this piece of that. I'm going to get rid of that part right there. I want to figure out this using this angle and this length right here. I want to find the length of this side. And then once you've got that, you subtract that from the length of the whole vine, which is 5 meters, to get your delta H. So you should be able to do that with your trig. Once you know the delta H, I know I've got PEG at the beginning, and then I've got KE final. This is a two-part problem. So I've got kinetic energy final right here. So I've got Jane that is going to shoot off to the side right here. And she's going to have some of that kinetic energy. And Tarzan's going to have some also. So we're going to go KE Jane and KE Tarzan. Because her mass is 50 kilograms, his is 80 kilograms, you're going to have to separate their two kinetic energies, because his kinetic energy now, his 80 kilograms and whatever amount of kinetic energy he has, is now going to go all the way up to this top part right here, where this is PEG final for Tarzan. So the second half of the problem is taking Tarzan's kinetic energy at the bottom and converting all of that into gravitational potential energy at the top of the swing right here. So this is the second part of the problem right here, but you need to figure out Tarzan's kinetic energy at the bottom of the swing right there. Okay, I hope that helps you to understand how to approach number 41. If you have questions, obviously Tuesdays and Thursdays, this one's due on Tuesday, so you might want to tune into our Tuesday or log on to our Tuesday hangout for my office hours from 9 to 10. Take care, guys. Stay safe and stay close to home.